All right, hello everyone. We'll be going over week three, question three on the worksheet. So we're given a DAG, and the DAG defines the relationship of uh, ancestor and descendants. What we want to do is for every node, we want to find its ancestor. Uh, for instance, in this graph right here, if we wanted to find each edge like this, as this is the ancestor pointing to the descendant. For 3, we will want to return 1 and 0. And for a more unique case of 5, the ancestors not only include its direct parent, which is 3, but it also includes 1 and 0. The parent's ancestor is also your ancestor. So to find everyone's ancestor, a really simple approach would be, we'll consider this a brute force approach. Okay, now we can reverse all of the edges. And for each node, we can run either BFS and DFS to see what node you can get to. And you can store it in an array for each node. We can just return that, which would be a array of list of the ancestor for each node, which it could also be implemented using a map, right? But that's a brute force approach. But earlier when we discussed this, we mentioned a property. Your ancestor's ancestor is also your ancestor. So for 5, instead of running a BFS, could we just find its parents and then just take the ancestor of the parents plus your parent to be to be all of your ancestors? Yes, that approach is correct under one condition. By the time you find your parent, we already have to know all of the ancestors of your parents. For example, if we search on 5, the ancestor of 5, we see that's 3 plus ancestor of 3. If at this moment we don't know that the ancestor of 3 is 0 and 1, we would have to do a search to find 0 and 1, and that would be a BFS like we did earlier. So is there a way to make sure that 3 is searched before 5? And for every case like this, is it possible to have all of the parent search before the child does? Yes, it's possible. Why? Because in the problem definition, we see that the graph is a DAG. So by definition, a DAG exists if and the graph is a DAG if and only if there exists a topological sort. So if we do a topological sort from and we order it from the uh, elderly, the most elderly ancestor to the youngest person, then we would have a topological sort where we find all of the ancestor before the ascendants. So to search this for the descendants, we can just include the parents and the parents' ancestor. That would always exist. Um, yeah, so to find the topological sort, it's pretty easy. We can just go through the graph and find nodes that have no neighbors. Um, in this case, we see that there's no edge going into 0. There's also no edge going into 1, no edge going to 2. everything else, there's an edge pointing at them. We can find 0, 1, and 2 uh, in the topological sort. And after removing 0, 1, and 2 and their corresponding edges, we see that 3 and 4 would have no neighbors. And after removing the edges coming from 3 and 4, we'll see that 5, 6, 7 would have no in neighbors. So if we are able to process the nodes 0, 1, and 2 first, when we run 3, we know that their parents have already been processed, so we know about the fact of the parent's ancestor. In this case, they don't have any ancestor. When we process 5, 6, and 7, we see that earlier we wanted to process 5. We want 3 plus the ancestor of 3. But we see that 3 is processed before 5, and we can already just take the ancestor of 3 plus 3 to be the ancestor of 5. And that should not be a problem. And for 6, same thing. We see that the parent of 6 is 3 and 4. Just by checking in neighbors, we can just take, for 6, we can just take 3, 4, ancestor of 3, and ancestor of 4. The topological sort guarantees that ancestor of 3 and ancestor of 4 already exist. So to summarize, what you do is you build the graph going from parent to the child, and you first build a graph, directed graph from parent to child, and then you do a topological sort and store it into an array A, for example. And we can go in order of A. Using the property that ancestor is parent and ancestor of parent, plural parents. And after that, we can just return this, returning this ancestor list we just built right here. And that's it. On the worksheet, the solution is the brute force solution that we went over, and this is not ideal. So in a problem like this, I highly encourage you to, if you see DAG, for example, I highly encourage you to think about if there's any simplification that could be done using topological sort. And in this case, we're saving a lot of time because we don't have to do a DFS on everything. We can simply take the property that the parent's ancestor is also your ancestor. And that would save a lot of time in the computation. And that's what we want. And that's probably also the expected answer rather than this brute force solution. All right, I'll see you guys next time.